First thing you need to know is about our types of variation. So we covered this in 9.1. We're going to look at inverse variation. Inverse variation is our division variation. It follows the pattern of y equals k over x. So in these problems, we're asked to do two things. We're asked to use, again, information to write an equation that relates x and y. That means that it should have x and y in it as letters, but k should be filled in as a number. And then secondly, to solve for a particular value. So for question number 1, I'm going to start by using the values given in the problem. Y is 2, and then k we don't know, x is negative 2. We can solve that for k by multiplying both sides by negative 2. That in itself is not an answer because the directions don't say find k. They say write an equation that relates x and y. So that equation would be that y is equal to negative 4 divided by x. And the second thing it says to do is says then find y when x equals 4. So plug a 4 in for x, and we get negative 1. Okay. So first use the given values to find k, but k itself is not an answer. The equation with k in its spot is an answer. And then use the value given in the directions to find a new answer for y. Questions? I'm going to skip over number 2 and go down to number 3. Same type of problem, but here we're using joint variation. Our joint variation relationship is z is equal to kxy. Same type of problem. We're going to start with the given information. Z equals kxy using the values from the problem to find what k is. So 8 times 2 is 16. Divide by the 16 gives negative 1/8 for our k value. But k itself is not an answer. Our answer is the equation with k in its spot. Then use the values in the directions to find a new answer for z. So z is equal to negative 1/8. The directions say x is negative 1 and y is 4. 2 negatives make a positive, and 8 times 1 times 4 gives 4/8 or 1/2. Questions? All right, we're going to go ahead and skip ahead to the next type of problem. It'd be a good idea to try those two problems on your own at some point, but I think there are probably bigger concerns later, so we'll move forward to the other types of problems. The next thing we studied in sections 2 and 3 were the graphs. So we in these are asked to give our asymptotes, the types of asymptotes that we have, and then to plot the function. Our rules for asymptotes. Vertical asymptotes are numbers that make the denominator equal to 0. We're not allowed to divide by 0, so that causes a break in our graph, and that break is the vertical asymptote. Okay, so to find vertical asymptotes, we're going to be looking for where the denominator equals 0. Horizontals, we have a couple of different situations we can come across. I'll talk about those as we hit the individual problems. For number 5, it's not in the correct format to be able to work with it. It's not a y equals, so we need to make it a y equals by dividing by x. So the equation we're going to use is y is equal to 1 over x. A vertical asymptote is then the number that makes the denominator equal to 0. So that's going to happen when x equals 0. Asymptotes are equations, they're not just numbers. So you need to have a letter in there as well, that x equals something or y equals something. A vertical is going to be an x equals because we're setting the bottom of that equation equal to 0, and there's an x in that. So we're solving for what x is. So our vertical asymptote is going to be an x value. For horizontal asymptotes, there's a 3-part rule. And this is if we have just one fraction. We look at where the power is bigger. Okay, power bigger on the top means none. Power bigger on the bottom means y equals 0. Power same means y is equal to a over c, where a and c are the numbers in front of those x's, or x squareds, or whatever that highest power is. Right, and those notes for this are in section 3. They're in your section 3 handout. So for this problem, the power is bigger on the bottom, because on the top we don't have any x's, on the bottom we have a first power of x, so the power is bigger on the bottom, which means we have a horizontal asymptote at y equals 0. So we can plot those asymptotes into our graph. Then to actually create the graph, you may graph it on your calculator and sketch in the curve. Okay? So on your calculator, just type in the function, and you'll see it looks like this. Okay. So our asymptotes are things we need to think about by hand, and then the graph of the curve itself you can do on your calculator and just sketch it in.
So because there's no x on the top of that equation, then the x on the bottom is bigger.
Right.
But if there was an x squared on top, it would be
Then that would be bigger. Yep. We're looking for the highest power of x. So 1x is more than no x. For the next one, vertical asymptotes are where the denominator is equal to 0. So we'd want to say, where does x minus 1 equal 0? And that is where x is 1. So our vertical asymptote happens at x is 1. Now this problem is a little bit different in finding our asymptote. We can still find our horizontal asymptote for the front of this thing. So in this fraction, where is the bigger power of x? On the bottom, which means what?
0.
Y equals 0, but then there's this plus 2. So our asymptote is going to be at 0 plus 2, or 2.
What is the power on, that's bigger on the bottom end?
That we don't have any x's on the top, and we do have an x to the first on the bottom. So we're looking for the highest power of x. If there's no x's, that's like an x to the 0. And the x to the first is bigger than that. Okay, so then on this one, because of that plus 2, we can find the fraction part of it has an asymptote at 0, but then we have that plus 2, so we just add the 2 to that. So our horizontal asymptote comes in at a height of 2. And then you can plug the function into your calculator. When you do so, make sure whatever you are dividing by, you put parentheses around. That makes a very big difference in your graph. Okay? We need parentheses around anywhere in a fraction where there's more than one thing going on. It wasn't important in the last one because it's just a 1 and just an x. Okay? But wherever there's more than one thing going on, you need parentheses around that. So let me do that. We'll see it looks like that. We have some more graphing examples, but I have to scroll to get to them, and then I'll lose all these notes. So are there any questions on the notes that are there, those examples? Okay, so for number 7, vertical asymptotes occur where the denominator equals 0. So we set the bottom equal to 0 and solve. We get x equals 4. Horizontal asymptotes, we're looking for the powers of x and where it is bigger. We have an x to the first on the top, and we have an x to the first on the bottom. When the powers are the same, we take the fractions of what's in front of those x's. In this case, that is 1 over 1, or just y equals 1. Okay, when the powers are the same, they both get to play a part in making the answer. So we take the fraction of the coefficients of those. Again, you can plug it into the calculator to create the graph, but make sure you would put parentheses around that x minus 4. Otherwise, your calculator is just going to divide by x and then subtract 4. And we want it to divide by all of that. So we need to put parentheses around that to group it together. Do that, something like this. Number 8, vertical asymptotes happen where the denominator equals 0. Divide both sides by 2. Take a square root. We get x equals 0. Horizontal asymptotes, we're looking for where the power is the biggest. So where's the power the biggest here? On the bottom, and the rule is when it's on the bottom, we're going to get one at 0. And then we can plot it on the calculator. This one looks different than the others. Because of that squared, they both end up on top. For number 9, vertical asymptotes happen where the denominator equals 0. So that's at x is 1. Horizontal asymptotes, we're looking for the biggest power. So where's the biggest power on this one?
Top.
On the top, and our rule is then that there is none. Don't just leave it blank, because then I won't know whether you didn't know or whether you knew that it was none. Okay, so actually say you know that there is not one. So vertical at 1, and I don't remember what the graph of this looks like. All the other ones I can graph in my head, but this I cannot. And again, make sure on this one that you put parentheses around that x minus 1. Otherwise, you will get a very different answer. Okay. Questions on the asymptotes or graphing? The next part says perform the indicated operation, which means there's all different types of arithmetic that's going to show up in these problems. So we want to pay attention to whether we're adding, subtracting, multiplying, dividing. And then we want to make sure that our answer is as simplified as it can be. When we multiply fractions, we multiply together the tops and the bottoms. We do not cross multiply. Okay? The danger of students learning cross-multiplying is once students learn to cross-multiply fractions, they cross-multiply every set of fractions they see. Cross-multiplying fractions solves an equation. If it's not an equation, it is not a time to cross-multiply. Okay? So there's no equal sign in this. When we multiply fractions, we multiply the tops, we multiply the bottoms. Then we want to reduce where possible. So 6 and 3 can be reduced. And I can cancel out 2 of those x's with 2 of the x's in the bottom, which leaves just a 2 on top and an x squared on the bottom. Number 11 is a multiplication problem. You cannot cancel parts of additions and subtractions. So I cannot go in this and start canceling off those x's. Okay? Not allowed. Not allowed, not allowed. Do not cancel part of additions or subtractions. Division undoes multiplication. It doesn't undo adding. So we can't cancel part of an adding problem. We can cancel part of a multiplication problem. To turn this into a multiplication problem, we need to factor where we can factor. X plus 2 cannot be factored, so I'm just going to group it up. But this denominator can be factored. What multiplies to 4 that adds to 4?
2.
2 and 2. Then I don't need that old one anymore, I can cross it out. Now I can cancel whole groups of multiplication that match. So I can cancel an x plus 2 group, and I can cancel off one of these x's with one of those x's. Which leaves x to the 4th on top and an x plus 2 on the bottom. But I cannot cancel off one of those x's because that would be canceling part of an adding problem. And dividing does not undo addition. Questions? The next problem says divide. We divide fractions by flipping over the second one and multiplying. And again, when we multiply, we cannot cancel part of an adding or subtracting. So I'm going to group up the x minus 3's. And since those groups exactly match, I can cancel the whole group, but I can't cancel just part of an adding or subtracting. I can cancel off one of those x's, and what does it leave? So there's two common answers to this question. One is right and one is wrong. One common answer is 2x. One common answer is 3. So what do we think it is? 3. We're canceling off the x, the coefficient remains. We're not subtracting. 3x minus x is 2x. Right? We're dividing off the x, which leaves just that coefficient. Questions on multiplying or dividing? (13) is an addition problem. What do we need before we can add or subtract fractions? A common denominator. These ones have a common denominator, so they're set to go. So on the tops, we're going to combine like terms, 7x plus 2. And on the bottom, we do not add the denominators. The denominator is the common denominator. Don't cancel the 2's, don't cancel the x's. That's part of an addition or subtraction problem, and we can't cancel part of adding or subtracting. It always makes me sad when I see students like have a right answer and then do wrong things to it because you were there and then you messed it up. Number 14 is a subtraction problem. The first thing I do on a subtraction problem is change it to plus and tie that negative to the second numerator. Then to add or subtract, we need a common denominator, and we do not have one. So we need to factor where we can factor. How does x squared minus 16 factor? That's our difference of squares. So that will be our common denominator because that covers everything that shows up in the bottom of fractions. Take down the old numerator. And if any changes are made to the denominator, make those same changes to the numerator. In the first fraction, the denominator is exactly the same as it used to be, so the numerator gets to stay the same. The second one, bring down the old numerator, and what changed? An x minus 4 showed up, so it needs to come into the top as well. To finish this up, I have my first numerator is fine, but my second numerator I need to distribute, and I need to distribute the negative 1. That's why we attach that negative to the 1 as our very first step. So I distribute the negative to make negative x plus 4. This is where I get lazy and say it's all over my least common denominator. As my final answer, combine like terms all over the least common denominator. Questions? The last problem here is a multiplication problem. I cannot cancel parts of additions and subtractions, so I need to start by factoring. So 16x to the 4th, that's just one thing, it can't be factored. 4x plus 16, what do they have in common?
2, 4.
4. So that leaves x plus 4. And then I don't need that old one anymore. 3x plus 12, what does that have in common? 3, which leaves x plus 4. And then I can cancel out stuff that matches. X plus 4's match. There is more stuff that can be canceled, but I find for myself right now there's actually a lot of different things that can be canceled, and if I start trying to cancel them, I usually end up canceling too much or not enough. So what I do at this point is treat it like question number 10, multiply it together first, and then do all of the reducing. So on the top I have 16 times 3, which is 48, and x to the 4th. On the bottom, I have the 4 that's all the way in the front, times the negative 4, so that's negative 16, and x to the 5th. And then we're going to reduce this down. 16 goes into 48 3 times. I can take out 4 of those x's, which leaves 1 on the bottom. So I'm left with 3 over negative x. It is fine with me if you want to skip that step of multiplying it together first and just start trying to cancel stuff within the problem, but I just find for myself that I end up missing something, or I cancel the same thing twice, and somehow I usually end up messing it up. So I just like to get it all together first and then do my reducing. Questions?
You leave that there.
The next type of problem we're going to look at is simplifying the complex fraction. When we simplify a complex fraction, we're going to multiply each part of it by the least common denominator. So there are 4 parts to this problem. Each of those little fractions is its own part. And we need to multiply them all by the same thing so that it's not really altering the problem. It's just changing the way it looks, but the value is maintaining the same. So what are we going to multiply that will cancel everything that's present in any of those denominators? What kind of a number do I need to be able to cancel them?
2.
So what number will be able to cancel a 6, a 12, and a 2?
3. 2. Oh.
A least common denominator will always be at least as big as your denominators. So 12 will be able to cancel off a 6, a 12, or a 2. And then in the denominators I have either x's or x squareds. So how many do I need? X squared. I don't need to accumulate all of them. I just need enough so that it will individually be able to cancel each one. Okay, when we're coming up with our least common denominator, we're looking for what is large enough to be able to cancel what's in each of the parts. So then as we go through and cancel, in the first one, the 12 cancels with the 6 to become a 2. The x squared cancels the x squared. So on that, I am left with then just a 2. In the next one, there's nothing to cancel with the 12. It can't cancel that 2 because they're both on tops. But I can cancel off the x with one of those x's. So I'm left with a 2 times 12x, or 24x. We can only cancel off the denominators. So in the next one, I can cancel off the 12 in the denominator, and I can cancel off one of those x's. So I'm left with a 4 and an x. And the last one here, I can cancel off the 2 with the 12 to make 6, the x squared and the x squared. So I'm left with a 3 and a 6, or 18. What do you notice about all the numbers in the problem? They're all divisible by 2. Since they are all divisible by 2, we can divide them all by 2. If it's some and not others, you can't do it. But if everything can be reduced, then you can reduce. Questions? Number 17 has 3 parts to it. What do I need to multiply that has enough power to cancel off everything that's in the bottoms? 3 times x plus 1. So in the top one, the x plus 1's go. Leave the 10 and the 3, which we multiply to make 30. First part of the bottom, the 3's go, which leaves 1 times x plus 1, or just x plus 1. If this numerator was anything other than 1, like say it was 5, we would need to distribute, right? 5x plus 5.
Why doesn't that other x plus 1 go?
I haven't done the last one yet.
Oh.
It will. So then in the last one, the x plus 1 goes, and we are left with the 2 and the 3, which makes 6. This isn't quite as clean as it can be, because we can add and get 7. Super common mistake that students would make on a problem like this is canceling that 6 with the 30. Okay? And again, this is one of those places where it makes me sad because you were totally on the right track and then you do something at the end that messes it up. We can't cancel a part of an adding or subtracting, so we can't cancel off that 6 because it's being added to stuff. Okay? So we can't reduce that, but we can add a 1 plus a 6. Questions? Last type of problem is solving an equation. The first equation that's here is a proportion. It is 1 fraction equals 1 fraction. When we have a proportion, we can solve by cross multiplying. 2 times x squared minus 18 equals x times x, or x squared. Distribute that 2 through, so I get 2x squared minus 36. I'm going to subtract my x squared to get them all together. You have 2 options for solving this. Since it is quadratic, we could solve it by factoring. Or, since there's no x term on it, we could add the 36 to both sides and take a square root. That's usually what most students think is the easier way, but a warning about doing that. If I add 36 to both sides and I take a square root, what do I get for my answer? Plus or minus 6. And that's the warning on that, is most students will forget the plus or minus, and then you're only getting one of your 2 answers. Whereas if you solve by factoring, this factors as x plus 6 and x minus 6, so then we can see both of those solutions coming in. Okay? I don't really care which way you solve it. They're both completely valid ways. Just make sure you don't forget a plus or a minus if you need it. We would want to confirm that plugging those in don't make us divide by 0 at all. So I would want to double check that, and I can see that plugging in a 6 or a negative 6 will be fine. So they are both solutions. Number 19 is not a proportion because I have that addition in there. It's not just one fraction equals one fraction. So we solve this by multiplying the entire equation by the least common denominator. The least common denominator is a really big theme in this chapter, right? That's a huge objective, to be able to find the least common denominator here. We need least common denominators when we add, we need them when we subtract, we need them to simplify the complex fractions, and we need them to solve the equations. So least common denominator is a big theme and a really big objective for the chapter. What is the least common denominator for this equation? X times x plus 4. We need everything that shows up in any of the denominators. And an x alone is different than an x that has stuff added to it. We multiply that by each part of this equation. When I multiply the first fraction, the x plus 4's cancel, so the 15 and the x are left over. When I multiply the second one, the x's cancel, which leaves the 5 and the x plus 4. And do not forget to multiply the 5. We have to multiply the entire equation, even if they're not fractions. You have to multiply every single part. To solve this, I need to do some distributing. I'm going to combine some like terms here, so I get 20x. Let me put those together. I'm going to subtract 20x from both sides. Which leaves 20 is 5x squared. It's quadratic, so I could get everything on one side, set it equal to 0, or since it's just an x squared, we can divide by 5. We get 4 equals x squared. So take a square root, and I get x equals plus or minus 2. Neither one of those will cause us to divide by 0, so they are both valid solutions.